In this video, we'll describe the Rankine cycle. Now, the Rankine cycle is a specific type of the vapor power cycle. A power cycle is a cycle whose vapor power cycle is a power cycle whose working fluid experiences phase change, but is a vapor during the power production process. So our power production process for the power cycle is going to normally be a turbine. So that means it's going to be a vapor as it goes through the turbine. So we're dealing with gas turbines, not hydro turbines. Now, the Rankine cycle is a specific type of vapor power cycle, and it is the ideal vapor power cycle. By ideal, we mean a few things. We mean first that all work devices are adiabatic and reversible. All heat transfer devices are isobaric and reversible. All connections, so those are the lines that connect the work devices and the heat transfer devices together, those are adiabatic and isobaric, so no losses along the lines. We're also going to, for a Rankine cycle, assume that water will enter the pump as a saturated liquid. Unless stated otherwise, we'll assume that steam enters the turbine as a saturated vapor. This is going to be our conditions for a Rankine cycle. So let's look at how a Rankine cycle will work. So we have a diagram of the Rankine cycle on the left. We have the vapor dome on the right, and underneath we have a table we're going to fill in for some of the equations for the processes for the Rankine cycle. So like we said before, at state 1, the quality is going to be 0. And we can see here on the vapor dome, we're on the saturated liquid line at this low pressure setting. So before we come into the pump, we'll be at a low pressure line. And so we'll go through a pump. And so the purpose of the pump is going to be to do compression to increase the pressure of our liquid. So because it's an isentropic pump, we can see here on the vapor dome that since this is temperature versus entropy, the entropy is constant. It goes straight up until it gets to the next pressure setting, which is the high pressure for the pump at state 2s. So across this pump, we analyze with first law, and for all these first law analysis, we're going to assume that the kinetic and potential energy are negligible. These are one exit systems. So we're going to reduce it to the heat transfer across the pump minus the work of the pump is going to equal to the change in the enthalpy. Well, we said all of our work process will be adiabatic, so that heat transfer is going to go away. And so we can rewrite this as the work is equal to enthalpy at state 1 minus enthalpy at 2s, or remember for a pump, because we're going to assume that it's incompressible, we can rewrite this as the specific volume 1 is going to equal the change in pressure from pressure 1 to pressure 2. And that will be the work done by a pump, an ideal pump in this case for the Rankine cycle. Okay, so now we're at state 2s. We need to get to state 3. It's going to go through the boiler. Boiler is sometimes also known as a steam generator, and the purpose of the steam generator or boiler is to add heat to our system. So we're going to add some heat. We're going to add this heat using constant pressure. So since it's constant pressure, isobaric, that means that we're also going to state that the quality at state 3 is going to be equal to 1. So it's 100% liquid. So it's right there on the saturated liquid line. Well, it's isobaric, constant pressure, so that means that on the vapor dome, it'll follow the path along that constant pressure line until it gets to state 3 on the saturated vapor line. So that gets us to state 3. So if we analyze the conservation of energy for this boiler, again we write the equation simplified for the boiler. It's a boiler. All it's doing is adding heat, so there's no work. So we get rid of the work term. We can rewrite that as the specific heat transfer from 2s to state 3 is equal to the enthalpy at state 3 minus the enthalpy at state 2s. So now we're at state 3, we're trying to go to the turbine. So our turbine, the purpose of that is it's expanding. So it's now taking all that high pressure, that high energy vapor. It's going to expand, and through that expansion we're going to get work out of it. So we're going to have work coming out of the system. It's going to turn a turbine. All right. It's going to be isentropic. again. So we can see here on the vapor dome that our process goes straight down. There's no entropy change to 4s. So we can actually see right in here that in this case, if we, for a Rankine cycle, if we go to state 3 and it's on the saturated vapor line, then we are definitely going to be in the saturated mixture region as we come down here. Okay. So then we do the conservation of energy for the turbine. Again, it's a adiabatic device, so heat transfer is going to go to 0. We rewrite it in terms of a positive work, so work 4s is going to equal to enthalpy at state 3 minus enthalpy at 4s. And lastly, we're going to go through our condenser. So the purpose of the condenser is to remove heat. Why are we getting rid of heat? Because we want to get back, or it's a cycle, it needs to get back to that original state. So we're going to get rid of whatever heat was left in there so we can get back to the original state before the pump. Another thing to consider about this is that we want the pump, before things go through the pump, it needs to be back to a saturated liquid. If you have vapor going through your pump, you get what's called cavitation. It damages the pump. So we want it to be all liquid before it gets into the pump. So we're going to reject some heat. Right, remember again, for our heat transfer devices, it's going to be isobaric. So we're going to follow this constant pressure line until we get back to state 1. So we look at the conservation of energy. Again, in this case, it's a heat transfer device, so there's no work being involved, so the work term goes away. We rewrite as the heat transfer 4s to 1 is equal to enthalpy 1 minus enthalpy 4s. Now for these equations, for the pump process, we should, according to hip to win, the work is coming out of this system. The work is coming into this system, because the pump, we add work and we get a pressure change in there. So since work in, win, work in, so this should be negative. For the steam generator, we're adding heat in positive, so this term should be positive. For the turbine, now the work is coming out, we are generating work. So if the work in is negative, then work out is positive. And finally, for our condenser, the heat is going out of the system. We're rejecting the heat. So hip, since heat in is positive, therefore the condenser, this term should be negative. Finally, we're going to talk about a Rankine cycle with superheat. So before we were talking about where the steam enters the turbine at saturated vapor line. Well, if you have superheat, that means that you are adding so much heat that the heat transfer produces superheated vapor at state 3. So what this would look like on your vapor dome is now the boiler has taken it beyond just the saturated vapor line, taken it all into superheated region. Now when you come down to state 4s here in this case for the ideal system, it depends on how superheated you've made it. Now you could just superheat it enough so that when you come back down, maybe you're in the saturated mixture region when you go to 4s. Or you could superheat it enough that you are going to still be superheated when you come to state 4s. It all depends on how superheated you get it.